So let's do a review so far of the steps that we've encountered in creating our spanning tree. Step number 1, we need to figure out who the root bridge was. Step number 2, on every switch that was not the root bridge, we had to select something called a root port. And now in step number 3, after each switch has determined its own local root port, then a designated port is determined for each collision domain. Now we already talked about designated ports back when I talked about electing the root bridge. So let's go back to this diagram, something new. So if the switch in the middle is my root bridge, we already know that every single interface he has for that broadcast domain, because remember switches do this on a per VLAN per broadcast domain basis, is going to be forwarding as a designated port. And now we know that step number 2 was we went to each switch to figure out what its root port would be. So here's what I want you to do. I want you to pause this video right now and then figure out what the root port is for all the remaining switches. And when you think you've got that determined, press play. Oh, before you do that, I suppose you need to know what the bandwidth values are, because these colors don't necessarily mean anything by themselves. So I typically have black lines for fast Ethernet and red lines for gigabit Ethernet. So I'm relying on you remembering what the cost values were. If not, you might need to look that up in the previous video. But go ahead and pause this and figure out which interfaces are root ports. All right, so I'm assuming that you paused it, you figured out which ports were root ports. Let's see if you were right. You could start really from any switch. I typically recommend starting from a switch or bridge that's physically connected to the root bridge. So let's just start over here with 4411. So if he uses port number 3, that's going to be a cost of 19. If he uses port number 1, I know it's going to be greater than 19 because it's going to be 19 plus something else. But if he uses port 6, that's 4 plus 4. So it's a total cost of 8 2 gigabit links. 4 plus 4 is 8. So he's going to select port 6 as his root port because that's the lowest cost port. 55FE down here, I think we can pretty much safely assume that his port number 8 will be his root port because that's a cost of 4. Every other path he has is larger than that. If we move over here to CBCC, we have the same thing. It's 19 going straight down. It's going to be 19 plus something going across, so we can rule that out. But it's going to be 4 plus 4 going this way, so it's going to be 8. So we can mark that as our forwarding root port. AAEE, that's going to be his forwarding root port because that's a cost of 4. Now, here's where we get into something that you may have scratched your head with. 7789. He actually has a tie. If he goes, let's change this here. If he goes in this direction, it's 19 plus 4, so it's 23. And if he goes in this direction, it's 19 plus 4, which is 23. So we have equal cost path, and yet only one of them can be the root port. In that particular scenario, when that is the case, remember, how did he learn about these paths in the first place? Because he got a BPDU from the sending bridge ID of this, and he got a BPDU from this guy that had a sending bridge ID of that. So if the costs are the same, he takes a look at the sending bridge ID of his two neighbors, and he says, which of my neighbors has the better name, has the lowest sending bridge ID? In that particular case, it would be 02. 02 is lower than 0A. So 02 would be the winner. So the port leading to him would be the forwarding root port. So now we got our root ports done. So that was step number 2. And then step number 3 is our designated ports. And this is just a repeat of what we looked at before when we were talking about the root bridge back in step number 1. Every collision domain requires one designated port. So if we go back to our whiteboard here, we can check off, for example, we know that this is done because there's a designated port. This collision domain is done because there's so these 4 cables are finished, because we already have designated ports there, so we don't have to figure it out. So the cables for which we need to figure out who the designated port is that cable, that cable, that cable, that cable, and that cable. Those 5 cables right there. And I'll give you a hint. Here's a little trick. If you have a point-to-point link where you have a cable and there's just one switch on one side and one switch on the other side, if you've already determined that one of the interfaces on that cable is a root port, guess what? By default, the other end of that cable has to be a designated port. Has to be a designated port. And like down here, this has to be a designated port. Well, why is that? Because remember what the definition was of a designated port, how we determined it. It was the port on the cable that had the least cost path back to the root bridge. So if I go back to this, switch 4411. The best cost he has to the root bridge is 8, right? 4 plus 4. The best cost he had was 8. But at the other end of the cable, the best cost 55FE has is 4. I'll put this right here. My best cost to root equals 8. This guy says my best cost to root equals 4. So if these two are fighting it out, 55FE is going to win, and he will end up being the designated port. So he'll go forwarding as a designated port. All right, what about between 55FE and 7789? Well, 7789 at the bottom, he says my best cost, which is based on the root port, to root equals, what is it? 23, 19 plus 4. So between 55FE and 7789, 55FE is the winner. He's got the lowest cost path back to the root bridge. So that interface on that cable will be the designated port. And then if we go over here to AAAE, he says my best cost to root is 4. So between AAEE and 7789, well, oh, wait a second. Remember that? How I said if you have a root port on one side, the other side is already a designated port? Well, now you know why. So if we take a look at this, you see, if we had just used sort of my cheat sheet method, we would have said, okay, Keith told me that whenever there's a root port on one side, the other side has to be a designated port. And now you can understand why. Because this port here is closer to the root bridge than this port. Same thing, between these two cables, we know that port 14 is going to be our designated port. Forwarding designated port. And why is that? Because AAEE has a cost of 4 to the root, whereas CBCC, the best cost he has is 8, and 4 is lower than 8. So at this point, oh, we got one more, this top cable here. Ah, interesting, we have a tie, don't we? 4411 has a cost of 8, CBCC has a cost of 8. So when there's a tie, how do you think we fix that? Do you remember how I said we fixed the tie down here on 7789 back when we were determining his root port? We said we took a look at his neighbors and figured out what the lowest ID was. Same thing right here. Since these guys recognize they have an equal cost path to the root bridge, they're going to look at each other's names and see who has the lowest bridge ID. In this case, A14 is lower than A1C. So because A1 is 4 is lower, he gets the privilege of being the designated port on that cable. He wins. So now what do we do with what's left? Well, when it comes to port roles, we have designated ports, which we've already figured out. We have root ports, which we've already figured out. So the last port role we have is what's called a non-designated port. So designated ports are always forwarding. Root ports are always forwarding. Guess what non-designated ports are? Yes, blocking. So we can take a look at our topology diagram now, and for every port that's not labeled as either a root port or a designated port, we can block it. So I'm going to block port number 2. I'm going to block port number 4. I'm going to block port number 10, and I'm going to block port number 3. So I'll put some squares around those so you can easily recognize them. And now with our blocked ports, we are done with our spanning tree. We have now blocked all potential loops. So in this particular case, if I have any two hosts, for example, let's say I have a host right here. Let's just say it's X connected to that guy, and I have a host right here, which is Y connected to that guy. There's only one path these guys can take that's forwarding all the way, which would look like this. Down here, through here, over, and up. That's the path that these two would take to talk to each other, because every other path they could take is going to run into a blocked port somewhere. So that's how we figure out our spanning tree topology. In the next video, we're going to take a look at some show commands. When I'm on a Cisco switch, how do I tell what its bridge ID is? How do I tell who he thinks the root bridge is? And then we're going to take a look at some commands where I can deterministically set this thing. Most people, if there's only one thing they do with spanning tree, they say, I want to make sure this switch right here is my root bridge. So generally the design recommendation is try to make your root bridge, like in my picture right here, in the center of the network. Ideally, it would be a core switch, a really big, beefy, fast switch with a lot of memory, and it should be in the middle of the network. You don't want some access layer switch that's in a wiring closet somewhere connected to a bunch of offices being your root bridge. It should be something in the middle. So how do we do that? Well, in theory, how we do that is we lower the priority. We know the bridge priority is the first thing that's looked at in root bridge determination, and that is a configurable field. So if we just go on that one switch and lower his priority to something less than 32.768, now he will be the root bridge, and everybody else will know that. And a lot of times that's the only thing that people do with spanning tree is they deterministically set the root bridge. But we'll look at a few other things we can do as well.